This is chapter 9, Momentum and Collisions. In this chapter, we're going to learn about something called impulse and momentum. Both concepts have to do with when things contact each other. This car crash here is an inelastic collision. The things that collide stick to each other. We'll also learn about elastic collisions when the things that collide bounce off each other.
The definition of linear momentum, P, is P equals mv, where m is the mass and v is the velocity. And the little arrow there just means vector. Arrow above the P and the arrow above the V. It's the symbol for vector. And you might wonder, well, why P? Uh, why not M? I guess one obvious reason would be that M was already taken, since it means mass, but an even deeper reason is that the original Latin term for momentum was impetus, and so P is a significant letter in impetus, and it makes sense to use it. In any case, the units of momentum are kilograms meters per second. And that makes sense because the units of mass are kilograms and the units of velocity are meters per second. So when you multiply mass times velocity, you get kilograms meters per second. Now momentum is a vector. Its direction is the same as the direction of the velocity. So just a quick review on vectors. Vectors always have both magnitude and direction. So the magnitude of momentum will be given to us by multiplying, of course, the magnitude of the mass by the magnitude of the velocity. But the direction of momentum is going to coincide with the direction of the velocity. Let's look at this train down here. Now, trains obviously have a great deal of momentum because they're so massive, and they often go pretty fast as well. So looking at this train, let's suppose that it has a mass of 10,000 kilograms. That's very light for a train, but this looks like it only has 3 cars. Anyway, it has a mass of 10,000 kilograms, and it has a velocity of 30 meters per second west. Therefore, the momentum, P, the vector P, equals 300,000 kilograms meters per second, because that is what we get when we multiply 30 by 10,000. Let's look at momentum and Newton's second law. Now we've seen Newton's second law before. We first started to examine it in chapter 4. And it keeps coming up because it's a very basic law, and many equations and formulas are based on it. In any case, how we are used to seeing it is the net force F equals the mass times the acceleration. Don't worry about that sigma symbol there. This symbol that I'm circling now with the mouse arrow is simply sigma. It means the summation of all forces, and it's just a fancy way to write the net force. So, if you have positive, negative forces, put them all together. Whatever the net force is, equals ma. All right, that's nothing new. Now, with a little algebra, we can rewrite Newton's second law as F equals ma equals m delta v over delta t. That, in turn, is equivalent to this next expression here that I'm circling with the mouse arrow, which is m delta v over delta t. And that is equivalent to delta mv over delta t. And of course, delta mv, since we're taking mv as a product, if v changes, well, obviously mv will change, so that we can bring the delta out. We get delta mv, which is simply delta p. Now, for those of you who don't really care about these derivations, you don't need to worry about it. But I do like to show them when possible so that we can see where things come from. So this means that we can rewrite Newton's second law as the net force equals delta P over delta T. That is, the net force equals the change in momentum over the change in time. So delta P over delta T. Now, you're not going to have to, or rather, you can still use F equals ma many times. It's just that for this lesson, it's going to be helpful to think of F equals ma as F equals delta P over delta T. The change in momentum over the change in time. Now, we're going to define a new concept, which is impulse. Impulse. Impulse is the average force times the change in time. So it's just force times time. All right, now, uh, we usually, some examples that we have of impulses, when we see a ball get hit by a bat, or a golf ball get hit by a golf club, or a person's head getting hit by, someone else's fist. There are many examples of impulse in life, but basically what it comes down to is force times time. If the force acts for a long period of time, it's going to be a big impulse. If the force acts for a short period of time, it'll be a small impulse. And interestingly, if you look at the units, all right, the units are Newton seconds, but Newton seconds is the same thing as kilograms meters per second. And that's simply because if newtons is the same as MA, which would be m times meters per second squared, well, then what we're getting here is we're canceling one of those s's in the denominator of the second squared and ending up with kilograms meters per second. And you'll notice that those are the same units as momentum. Kilograms meters per second, same exact units as momentum. We'll see why that's true in just a bit. Now, impulse is a vector in the same direction as the average force. Okay, so just as we saw that momentum was a vector in the same direction as the velocity, impulse is a vector in the same direction as the average force. Here are some real-life examples of impulse. Up in the upper left corner there, we have a baseball player hitting a ball, and actually it's a really nice swing. And this is an amazing photo. It gets the ball just when it's being compressed. Now, let's look at what happens with this baseball bat. You can kind of follow now with the mouse arrow here. I'm circling the point of contact. Well, we see that when the bat comes in contact with the ball, there is a certain amount of force, a large amount of force that the bat is exerting on the ball. And actually, keeping Newton's third law in mind, the force, these two bodies are exerting force on each other because it's always equal and opposite. But in any case, if we look at how this compression is working here, we can see that the bat is actually in contact with the ball for a certain amount of time. Now, it may be a short time, a very short time, but it still is a certain amount of time. And if the time is long, the impulse will be great. If the time is short, the impulse will be small, because impulse equals F delta t. Now, a cool little side note about this particular picture is I don't know how this happened, but I remember when I was in 7th grade, I was on a little league team, and they were called the Bears. And this guy appears to be on a team called the Bears, and he looks just like our star batter of that team. Uncanny how history repeats itself, I guess. Anyway, let's look at this other example down here at the bottom right. We have a boxer being punched in the face, and we see there's definitely a time of contact. The whole time that the boxer on the right's glove is in contact with the boxer on the left's face is time that would determine the amount of impulse. If it's a large amount of time, there'll be a great impulse. If it's a short amount of time, it'll be a small impulse. And so we can see the force actually distorting the face of the boxer on the left. Let's do some algebra again. If net force equals average force, which is delta P over delta T, we already proved that in an earlier slide. Well, then that means that we can multiply both sides by delta T, and we get F ab delta T equals delta P. And you'll notice that F ab delta T is the same as the definition of impulse, which we also saw on the previous screen. And so if F av delta t equals delta p, and delta p is simply the change in momentum, well then, the impulse is equal to the change in momentum. And that makes sense because impulse and momentum both have the same units, kilograms meters per second. And so we can also see how the impulse is just change in momentum. If impulse equals change in momentum, let's look at a specific example of this. All right, so whenever we're talking about changes in something, we're just talking about the final value minus the initial value. So let's look at this specific example. Let's suppose that west is the negative direction and east is positive. So if pi is negative 18 kilograms meters per second and pf is 12 kilograms meters per second, what is the impulse? Okay, first let's understand exactly what's going on in this problem. If you look at this green vector pi, all that means is initial momentum. P is momentum, I is initial momentum. It's a green vector. It's going west, and since we're considering west negative, it has a magnitude of negative 18 kilograms meters per second. That would be the mass of the ball times its velocity is simply negative 18 kilograms meters per second. Now PF down here, we can see that there has been a big change in momentum because it has completely switched direction. Okay, it's gone from a negative momentum to a positive momentum, and that has involved a great deal of impulse. Now, if we look down here at the green vector PF, this just, the P of course is momentum, F is final, and so the final momentum is definitely different from the initial momentum. And so if impulse is the change in momentum, then all you have to do is find out what that change in momentum is. And as usual, it's the final value minus the initial value. All right, well, take a second to just do this on your own. It's very simple. It's just a one-line type of problem. Try to calculate the impulse. And when you have an answer, you can resume the video. So pause it now and then resume the video when you have an answer. All right, so this is what you should have come up with. If impulse is change in momentum, then it's just the final momentum minus the initial momentum. And that's just 12 minus negative 18, which is 30 kilograms meters per second. We've successfully calculated the impulse. If the bat was in contact with the ball for 1 millisecond, what was the average force? All right, so again, part of the challenge of physics is taking your givens, figuring out what you're still trying to find, and then calculating it. So for practice, again, you should pause the video and try to do this. A hint is you're going to use the definition of impulse to try to figure this out. All right, so pause the video, get an answer, and then resume when you have one. Impulse is defined as F av delta t. We know that the impulse is 30 because we're given that, okay? And we're asked to find the average force. And then it tells us that there's 1 millisecond. You see the time as 0.001 because that is 1 millisecond. All right, so then just solving for FF, we get FF equals 30,000 newtons. And that would be the average force exerted on the ball. Now you might notice that that is a very large amount of force. Let's look at this practice problem. Hillary strikes a 0.058 kilogram golf ball with a force of 272 newtons and gives it a velocity of 62.0 meters per second. How long was Hillary's club in contact with the ball? In other words, how much time was that club head in direct contact with the golf ball? Okay, if you look at this picture here, you kind of see it right at that moment when the club head has met the ball. You can see the ball already being compressed, and the whole time that it's being compressed, it's also being accelerated. All right, so what we're looking at is how long this ball was actually in contact with the club. That's what you need to calculate. And of course, this is an impulse problem. So, look at your previous notes from this lesson. Try to figure this problem out. And resume the video once you have an answer. So pause now, try to figure it out, and then resume when you have an answer. Okay, let's go through the solution. We know that the mass is 0.058 kilograms, force is 272 newtons. Initial velocity is 0 meters per second. We know that because the ball was at rest, just sitting on the tee. And final velocity we're given. It's an impulse problem, so we write out the definition of impulse. It's F av delta t, and that is equivalent to delta p as we proved earlier. And F av delta t is the same thing as Pf minus Pi because, whenever you're getting delta, it's just final value minus the initial value. That means that F delta t, the impulse, equals mvf minus mvi because if P equals mv, then Pf is just mvf, and Pi is just mvi. So we have mvf minus mvi. Factoring out the m, we have mvf minus vi. Trying to solve for delta t now, we just divide both sides by f, and we have m vf minus vi over f. And now we can, as I like to say, plug and chug. You plug in what you're given, and then you chug through the calculation and get the right answer. And hopefully it is the answer you got. Now, if it's not the answer you got, you can, look through the solution and find where your mistake was. Now we're going to talk about the conservation of linear momentum. And this is a fundamental law. It's one of the most important laws of the universe. In the universe as a whole, the net momentum at any particular time is always constant. Okay, it's always constant because negative velocities and negative momentums cancel out positive momentums, and things are always going in all kinds of directions. But the basic law here is that linear momentum is always conserved. That is, P is always conserved. If the net force acting on a system is zero, its momentum is conserved. That is that the final momentum equals the initial momentum. All right, now we did see a conservation law already when we talked about the conservation of mechanical energy. You remember that one with PEF plus KEF equals PEI plus KEI. The same type of principle, because in the universe there's this basic law of conservation that applies to matter and energy, momentum, and all kinds of things. And if we look at the example I'm about to show you, you'll see how it relates to Newton's third law. All right, so as always, the best way to learn is by example. So let's look at an example. Let's say that we have a cannon, and it's a loaded cannon. It has a cannonball inside it. This is going to be a picture of before the shot is fired, and soon I'll show you a picture of after the shot is fired. But first let's look at before. All right, so the cannon is at rest with the cannonball inside. The momentum of the system is zero. Of course the momentum is zero because nothing's moving. So if velocities are zero, then momentum is zero. And that's why here, over here on the left part of the screen, I'm circling P sub I, the initial momentum, equals 0 kilograms meters per second. All right, now looking at the actual information of this example. We've got a cannon and a ball. The mass of the cannon is 500 kilograms. The mass of the ball is 10 kilograms. So the momentum is 0.
Now let's see what happens after the shot. So after the shot is fired, this is what the situation looks like. The force of the ignited gunpowder pushes the cannonball one way and the cannon the opposite way. The net momentum of the system is still 0. So it's pretty clear that the net momentum before the shot is fired is 0 because there's no velocity involved. But it's not always so clear why the net momentum after the shot is fired is 0. But we can see that it's true if we look at, if we set up PF, that is the final momentum,
we see that it equals the momentum of the cannon, which is m can v can, plus the momentum of the ball, the cannonball, which is m ball v ball. Now m can v can would be 500 times -3, and that of course is just -1500. But m ball v ball is 10 times 150, and that's 1500. They cancel each other out, and you get a net momentum of 0 kilograms meters per second. Just remember that you can always define which direction is positive and which is negative. It's usually easy to think of right as positive and left as negative, so that's what we did here. Now going back to what I said earlier about how this law is a consequence of Newton's third law. Well, for every action there's an equal and opposite reaction. We see here that a corollary of that really is that for this positive momentum that we have of the cannonball, we have an equal and opposite negative momentum of the cannon. Let's look at an example of cannon recoil. This is from a Civil War reenactment, and this is one of those old-fashioned cannons. Observe how when the shot is fired, there is a significant recoil. So you saw how there was that recoil there. There was an actual backward velocity in reaction to the bullets or the projectile's forward velocity. Another problem to examine conservation of linear momentum. At an ice skating rink, Ben and Erica stand at rest, and Ben pushes Erica, whose mass is 72 kilograms. Ben is sent in one direction at a velocity of 0.90 meters per second, while Erica is sent in the other direction at 1.2 meters per second. What is Ben's mass? All right, so based on what you learned in the last slide and what you learned earlier in this lesson, you should be able to figure this out. Pause now, try to figure it out, and then resume if you get stuck or after you get the answer. All right, so it's always good to do a sketch. You, of course, don't have to sketch with full color and nice drawing, but some kind of sketch to visualize is always helpful. So let's say that Ben is there on the left and Erica's on the right. We can label Ben's mass as M1, and we can label Erica's mass as M2, and that's given in 72 kilograms. So looking at the situation before the push-off, again, like with the cannonball example, there is a net momentum of 0 because there's no motion yet. So we can say that Pi equals M1 V1I plus M2 V2I equals M10 plus 72 times 0 equals 0 kilograms meters per second. Now, just to clarify something about these symbols, V1I, you probably figured it out by now. It just means the initial velocity 1. And velocity 1, of course, corresponds to Ben's velocity since he's M1. And velocity 2 corresponds to Erica's velocity because she's M2. And so V2 comma I means Erica's initial velocity. All right, now let's look at the situation after the push-off. And the problem tells us that after the push-off, Ben goes one way and Erica goes the other way. So you can choose which one's positive or negative, and that of course would probably depend on how you drew. But since I drew Erica on the right, I'm going to make her velocity positive, and since I drew Ben on the left, I'm going to make his velocity negative. So V1F, that is Ben's final velocity, equals negative 0.90 meters per second, and V2F, which is Erica's final velocity, equals 1.2 meters per second. Now M1 we're trying to find, M2 we're given 72 kilograms. Now at this point, if you didn't get the problem, you may want to pause again and see if you can figure it out. Or if you did get the problem, then just keep watching. All right, so the final velocity, PF, equals M1 V1F plus M2 V2F. That is the momenta of both bodies. And so that's just M1 times negative 0.90, Ben's final velocity, plus 72 times 1.2, which is Erica's final velocity. And that must equal 0 because we know that with the conservation of momentum, the net momentum before, that is the initial momentum, is the same as the net momentum after, which is the final momentum. So continuing on, we write down the law of conservation of linear momentum, Pf equals Pi. We write that Pi equals m1v1i plus m2v2i equals m10 plus 72 equals 0 kilograms meters per second. Pf, as we saw in the diagram, is m1v1f plus m2v2f. That equals 0. We know that from the law of conservation. And now doing our plugging and chugging, we put in negative 0.90, mass of Erica 72, final velocity of Erica 1.2, and that must equal 0. And then we can simply solve for m1. m1 equals 96 kilograms, so Ben's mass is 96 kilograms.
Now let's talk about momentum as it relates to collisions.
Now there are two kinds of collisions. There are elastic collisions and inelastic collisions. Let's learn about inelastic collisions first. So with inelastic collisions, momentum is conserved, but kinetic energy is not. That means that the momentum before the collision is exactly the same as the momentum after the collision. However, the kinetic energy before the collision is not the same as the kinetic energy after the collision. In inelastic collisions, the objects stick together after the collision. All right, so it'd be like throwing a wad of gum on the wall and it sticks. Or it'd be like hooking up Velcro to the front of your bumper car and then running into another bumper car that has Velcro, and the two stick after the collision. That's what an inelastic collision is when the objects stick after the collision. Now let's look at an example of that. Here we have an inelastic collision that's going to happen between two train cars. And you can pretend that there's some kind of like super glue on this part of the train car, which I'm circling now with the mouse arrow, and on this part of the train car, which I'm circling now with the mouse arrow. And so it's an instant bonding super glue. When the two surfaces connect, they're going to bond. All right, well, let's look at the situation before the inelastic collision takes place. We have mass 1, 5,000 kilograms, and we have v1i, that is the initial velocity of body 1, so v1i, equals 20 meters per second. On the right, we have mass 2 equals 5,000 kilograms, and v2y, the initial velocity of mass 2, is 0 because it's at rest. So let's look at the initial momentum and also the initial kinetic energy. Pi, so initial momentum, equals m1 v1i, and that equals 100,000 kilograms meters per second. You can verify that just by multiplying 5,000 by 20. All right, and then the kinetic energy, the initial kinetic energy, is 1/2 m1 v1i squared, and that equals 1 million joules. You can verify that as well by plugging in 5,000 for m1 and 20 for v1i. Now, the reason for both Pi and KEI, we didn't have to worry about M2, is that M2 is at rest, and so it has 0 momentum and 0 kinetic energy. The only source of momentum and kinetic energy before this inelastic collision happens is that of mass 1. All right, let's see what happens after the inelastic collision takes place. Both cars bond to each other, and then the combined mass of 10,000 kilograms continues to move east, but at a lower speed of 10 meters per second. So the final momentum, Pf, equals m1 plus m2, the combined mass, times that Vf, and that equals 100,000 kilograms meters per second. Notice that Pf equals Pi, because momentum is always conserved. However, if you look at Kef, that's 1/2 times m1 plus m2 Vf squared. And that ends up being only 500,000 joules. So there's a pretty big loss of kinetic energy. And you can verify the 500,000 just by plugging in 10,000 for m1 plus m2 and plugging in 10 for Vf. But there was a significant decrease in kinetic energy, although momentum remained the same. So with all inelastic collisions, momentum is conserved, but kinetic energy is not. Now there are various reasons for the loss of kinetic energy. The main one is the unseen deformation that goes into the bodies that stick together. Sometimes you've seen deformation happen, especially in car crashes. Um, but some energy gets dissipated into the deformation, into the heat of the crash, um, even into the making of the bond itself. So there are various reasons for the decrease in kinetic energy. But an interesting thing about conservation of momentum is that it's always conserved. All right, so let's look at this example problem. A 2,575 kilogram van runs into the back of an 825 kilogram compact car at rest. They move off together at 8.5 meters per second. Assuming that the friction with the road is negligible, calculate the initial speed of the van. All right, so I'm going to walk you through the beginning part of this problem, then I'll ask you to pause it and try to do it on your own. But let's just set it up first. So we have M1, 825 kilograms, and V1I equals 0 meters per second. And we have M2 equals 2575 kilograms, and V2I we're trying to find. Now, of course, you could have drawn the vans going the other way. That's perfectly fine. And then you could have assigned M1 to the van and M2 to the car, but as long as you keep your drawings consistent, it doesn't matter which way you go, especially because in the problem, it doesn't tell us in which direction the crash is happening, so you can just pick one. All right, so this is the initial setup. Let's look at the momentum before the crash happens. So Pi, initial momentum, equals M2 V2I, and that equals 2575 V2I, kilograms meters per second. As in the last example, M1 doesn't even figure in because it's at rest, and so it has zero momentum. Okay, now if we look at what happens after the crash, now obviously this is unrealistic because the compact car would have been crumpled in the back, but just for the sake of illustration, we have them like this, sticking together, okay, some kind of super glue holding them or whatever you like. But the combined mass of M1 plus M2, which is 3,400 kilograms, goes off at 8.5 meters per second as the problem tells us. All right, so this is just a diagram of what we're given, and the final momentum then is simply M1 plus M2 VF, and that is 3,400 times 8.5, which is 28,900 kilograms meters per second. All right, so based on the train example and what I've laid out for you here, you should be able to solve the problem. Just pause the video, try to do it on your own, and then resume if you get stuck or once you have the answer. All right, so let's go through the solution. We know that Pi equals M2 V2I, and that equals 2575 V2I. We also know that PF equals M1 plus M2 VF, and that equals 3,400 times 8.5, which is 28,900 kilograms meters per second. Now, since momentum is always conserved, the final momentum will be equal to the initial momentum. And so we have 28,900 equals 2575 V2I. And now we can simply solve for V2I. V2I equals 11 meters per second. So the van's initial velocity was 11 meters per second. And that looks like this. This is the initial drawing of the two vehicles before the inelastic collision happens. And the van's initial velocity was 11 meters per second. All right, let's look at some more examples of inelastic collisions. The ballistic pendulum. The ballistic pendulum was originally designed to measure bullet velocity because bullets are going very fast, and it's hard to clock them, especially before radar guns existed and all the things we have now. In the 18th century, the ballistic pendulum was invented, and it was useful for calculating high velocities. All right, so the way the ballistic pendulum works is the height to which it rises can be used to calculate the projectile's initial velocity. All right, so during the collision, momentum is conserved, even though kinetic energy is not. All right, in all inelastic collisions, such as this one, this is inelastic because the little m sticks to the big M. All right, well, kinetic energy will be lost. It's always lost in inelastic collisions. However, momentum is always conserved. So we can set up an equation to show that the momentum is conserved. Pf equals Pi. So m plus m times v loaded equals m times vi. Pf equals Pi. The final momentum equals the initial momentum. All right, so that's one equation that's going to help us to get that vi. But we're going to need another equation. And so that's what I'm going to talk about on the next screen. So after the collision, mechanical energy, Ke plus Pe, is conserved for the loaded pendulum. All right, so after the collision happens, we're still going to have the mechanical energy being conserved. Now I'm talking about the mechanical energy of the loaded pendulum. Notice that on the left we have a loaded pendulum, and on the right we have a loaded pendulum. No collision has happened. The collision has already happened. We're talking about what goes on after the collision, and what goes on after the collision is conservation of mechanical energy. And so we have KEF plus PEGF equals KEI plus PEGI. Filling in, we have 0 for KEF because on the right, that is a snapshot of the loaded pendulum coming to rest, so it has no kinetic energy. Plus PEGF, it will have potential energy, equals KEI, and there is definitely KEI because m plus m has a velocity, v loaded. And it doesn't have any initial potential energy because it's at the very bottom of the swing. So we have this equation, PEGF equals KEI plus 0. All right, 0 plus PEGF equals KEI plus 0. Now, just filling in then for PEGF, we have m plus mgh. That's gravitational potential energy for the loaded pendulum on the right-hand side there at its final location, equals 1/2 m plus m v loaded squared, which is the initial kinetic energy. All of that initial kinetic energy gets converted into potential energy. And so we end up with this equation, GH equals 1/2 V loaded squared. So the way you would solve this problem, right, is you'd measure H, you would then calculate V loaded, and then you would just work backwards into the equation we did on the last screen. Once you have V loaded, and knowing of course the mass of the pendulum big M and the mass of the projectile little m, you can calculate the VI. All right, so the ballistic pendulum is pretty neat. There will be a problem in class that's based on this, so make sure that your notes are complete. I can help you go through it as well. But it is kind of an interesting little contraption. This is a clip from something I found on YouTube of a guy who actually made a ballistic pendulum on his farm up in Idaho. Let's look at this guy's homemade ballistic pendulum just to see one in action. See, it swung back after the bullet was embedded. Watch again. Swung back. Okay, now let's see it up close. Notice how the angle gets measured at the top. And from that angle, the height can be calculated. I'll show you the trig for that in class. Slow motion. So as you can see, it is kind of a nifty little thing that the guy made by himself.
Okay, so I've done the
Yeehaw! All right. Let's go on then. Let's go on. And let's look at elastic collisions. In elastic collisions, both kinetic energy and momentum are conserved. The objects bounce after the collision. All right, so with inelastic, they stick together. With elastic, they bounce, like the billiard balls. And if you've played pool, you've seen those balls bounce. Those are elastic collisions. Now, of course, in real life, no collision is completely elastic nor inelastic, all right? Because even with the pool balls, some energy is lost in heat and noise when they bounce, and with a lot of inelastic collisions, they don't stick together perfectly. They stick together partially, and then they come apart. All right, so um, in real life, there is no completely elastic collision nor completely inelastic collision, except at the molecular level where you do have some completely elastic ones. But um, in real life, we don't really see those. However, it is important to study the ideal cases of completely inelastic and completely elastic, because that's how we learn about the conservation of momentum. All right, so let's talk more about these elastic collisions. If we look at this ball, if we pretend that it's a hard ball, like a pool ball falling on a hard surface, it's going to bounce back. The momentum will be conserved, and the kinetic energy will be conserved as well. We can see that the downward V matches the upward V, so we have conservation of kinetic energy. Now, a famous example of elastic collisions is Newton's cradle. You've probably seen it before. It was actually based on the writings of a different guy, not Newton, but Christian Huygens, who is a Dutch scientist. Christian Huygens, Huygens. Actually sounds like Huggins, which is where we get the English name Huggins. People who have Dutch ancestry, Huggins. I don't know if you've ever known a Huggins. In any case, it is called Newton's cradle because it's in honor of Newton. Let's see how it runs. Let's just look at this Newton's cradle for a few seconds. So notice what happens. The momentum is conserved and simply transferred to each end. All right, so it's pretty neat. You have the ball moving, and then momentum is conserved, and it's transferred to the ball on the other end. And at every moment, both momentum and mechanical energy are being conserved. All right, let's move on. Now, this is kind of a funny thing that I saw posted on Facebook a few weeks ago, and I think it's been floating around the internet, but it is kind of funny. This is a physics teacher on playground duty, using these kids as part of a Newton's cradle. Uh, I don't think he would last too long in his job, but in any case, it is kind of funny. Um, uh, maybe I could use this as an argument of getting out of playground duty. So we're going to talk about elastic collisions here, and this is an air track, two gliders on the air track, so they're gliding along without friction, and they've got these kind of bumpers on them so that after the collision they'll bounce. Elastic collisions, as you remember, are bouncy collisions, whereas inelastic are sticky. Okay, so let's look at the situation before the elastic collision happens. We've got M1 equals 8.0 kilograms, and V1I equals 3.0 meters per second going east. We have M2 equals 4.0 kilograms, it's at rest. And so if we look at the initial momentum, Pi equals M1 V1I, and that equals just mass times velocity, 8 times 3, 24 kilograms meters per second. The initial kinetic energy is 1/2 M1 V1I squared equals 1/2 8 times 3 squared, and that equals 36 joules. All right, so that's the situation before the elastic collision happens. After the elastic collision happens, we have this bigger mass of 8 kilograms still going on, but at a slower speed. And the small mass of 4.0 kilograms has been given a larger speed of 4.0 meters per second. Now, let's look at the final momentum and the final kinetic energy. The final momentum is m1v1f plus m2v2f. Notice both bodies are moving now, and so both will affect the overall momentum. And when you look at the final kinetic energy, you have 1/2 m1v1f squared plus 1/2 m2v2f squared equals 36 joules. plugging in the exact values, you see this. PF equals just 8 times 1 plus 4 times 4, which is 24. Notice that PF matches our PI. Momentum is always conserved. And we have KEF equals 1 half times 8 times 1 squared plus 1 half times 4 squared, and that equals 36 joules. Notice that kinetic energy was also conserved. This is true of all elastic collisions. Now, a neat little thing, just to point out, because it's actually going to help us to handle problems like this, is that the relative velocities are the same before and after. All right, let's look at what I mean by that. Okay, if you kind of look up at the top of the screen where I'm making this big circle there with the mouse arrow, all right, well, the relative velocity, that is the velocity of mass 1 relative to mass 2, is 3 meters per second. All right, but notice also down here, where I'm now circling with the mouse arrow, the relative velocity is still 3 meters per second. That is, if you look at the relative velocity of m2 in relation to m1, well, 4 minus 1 is 3, and so the relative velocity is 3. It's like, you know, if you're going on the freeway at 60 miles an hour, someone passes you at 80 miles an hour, their velocity relative to you is 20 miles an hour because it's 80 minus 60. All right, same principle. In elastic collisions, the relative velocities are the same before and after. All right, so this is a quick proof on that relative velocity thing that I mentioned in the last slide. If we look at the initial momentum, so the momentum before the collision, it's m1 v1i plus m2 v2i. And if we look at the final momentum after the collision, it's going to be m1 v1f plus m2 v2f. Okay, as always, the I stands for initial and the F stands for final. Now, since PI equals PF, since momentum is always conserved, we have m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f. Now we're going to rearrange things a bit. We have m1 v1i minus m1 v1f equals m2 v2f minus m2 v2i. We just swapped, really. All we did is we subtracted m1 v1f from each side, and we also subtracted m2 v2i from each side, and we ended up with this. Now we can factor out the m1, so we have m1 times v1i minus v1f equals m2 times v2f minus v2i. All right, now we're going to look at the energy side of things. The kinetic energy at the beginning, or before the collision happens, is 1 half m1 v1i squared plus 1 half m2 v2i squared. And the final kinetic energy is 1 half m1 v1f squared plus 1 half m2 v2f squared. All right, since with elastic collisions, kinetic energy is also conserved, we set these equal to each other, and we have 1 half m1 v1i squared plus 1 half m2 v2i squared equals 1 half m1 v1f squared plus 1 half m2 v2f squared. All right, now we're going to do a similar thing. We're going to swap things. So all we're doing is subtracting 1 half m1 v1f squared from each side, and we're also subtracting 1 half m2 v2i squared from each side, and we end up with this. It's just rearranging terms here, swapping sides of the equation. Now we can factor out from each side. We can factor out the 1 half m. So we have 1 half m1 times v1i squared minus v1f squared equals 1 half m2 times v2f squared minus v2i squared. All right, now we can drop the 1 half on each side, makes things a little bit simpler. And now we can use our Algebra 1 knowledge of difference of squares. That's something you learned in Algebra 1. And you have, since you have something squared minus something squared, that's a difference of squares. And that factors or expands to m1 times v1i minus v1f times v1i plus v1f equals m2 times v2f minus v2i times v2f plus v2i. Okay, moving along now in the proof. This is a key step, so watch what happens. We're going to use substitution. Okay, so we have this big term coming down, right? So if you look at the mouse arrow now, I'm kind of tracing this move, tracing it along the arrow. The M2 V2F minus V2I came down and replaced the M1 V1I minus V1F, because notice, if you look up here to this line of the proof that I'm now circling with the mouse arrow, you will see that we already proved that M1 V1I minus V1F equals M2 V2F minus V2I. And so what we've done is we just use substitution, and we have replaced this M1 V1I minus V1F that I am now circling with the mouse arrow. We've replaced this M1 V1I minus V1F with what that is equivalent to, which is M2 V2F minus V2Y. All right, so with that key step of substitution, we can now cancel like crazy, or as Mr. Halpin likes to say, do the mad Viking slash type canceling, and we get rid of a whole bunch of stuff. And so we end up with just V1I plus V1F equals V2F plus V2Y. And one last little swap of sides of the equation, and we have V1I minus V2Y equals V2F minus V1F. And thus we have proved that the relative velocities are always equal. Now, if you want to, you can memorize this bottom line here, V1I minus V2I equals V2F minus V1F. You can memorize it because it's always true. Or if you prefer, and it's probably a better idea, just accept the fact, now that you've seen the proof, that the relative velocities are always the same, and then you can determine your own order. I always like to do just the positive minus the negative at the beginning, and then it always comes out right. Then you can do the positive minus the negative at the end. But the point is that the relative velocities are the same, both before and after the elastic collision. This is a classic elastic collision problem. Ball 1 with mass 3 kilograms rolls with a velocity of 4 meters per second east. It collides with ball 2 with mass 5 kilograms moving 6 meters per second west. After the collision, what are the velocities of balls 1 and 2? Alright, so let's do a diagram. We have ball 1 here on the left, M1 equals 3.0 kg. V1I equals 4.0 meters per second. We have ball 2 on the right. M2 equals 5.0 kg. V2I is negative 6.0 meters per second. Y negative because it's going the opposite direction. All right, if we can always define our own positives and negatives, but it's kind of more intuitive to think of east as positive and west as negative. So that's what we're doing in this problem. Remember that in elastic collisions, momentum and kinetic energy are both conserved. All right, so we're going to keep that principle in mind as we solve this problem. And also, as I mentioned in the last screen, an interesting consequence of this is that the velocity of the balls relative to each other remains the same before and after the collision. And that'll become clear in this example as well. Now, if we look at this initial diagram, let's figure out what the relative velocity is. Well, this ball here is going 4 to the right, and this one here is going 6 to the left, which means that relative to each other, they're going 10 meters per second. Going 10 meters per second. All right. So the relative velocity in this particular case is going to be 10 meters per second. And that's because 4 meters per second minus negative 6 meters per second is 10 meters per second. Okay, so let's say that you were seated somewhere, like driving this 3 kilogram ball. Well, relative to you, that M2 ball is approaching you at 10 meters per second. Now, let's suppose you're seated on this M2 ball. Well, relative to you, on that M2 ball, the 3 kilogram ball, the M1, is approaching you at 10 meters per second. All right, so the relative velocities of these balls to each other, the relative velocity of these balls to each other is 10 meters per second. All right, so let's go through the solution. I'll go through part of the solution, then I'll let you do the rest on your own. This is our initial setup. This is our initial situation. We have our PI, that is the initial momentum, M1 V1I plus M2 V2I equals 3 times 4 plus 5 times negative 6 equals negative 18.0 kilograms meters per second. We also have our initial kinetic energy, KEI equals 1/2 M1 V1I squared plus 1/2 M2 V2I squared equals 1/2 times 3 times 4 squared plus 1/2 times 5 times negative 6 squared, and that equals 114 joules. The relative velocity, as I said in the last screen, is 10 meters per second. And we can just think of that as V1I minus V2I. It's going to be 10 meters per second. If we want that positive relative velocity, we simply start with a positive number and then subtract the negative to end up with a positive. Now let's look at the situation after. After the collision, you'll have something like this. Okay, you'll have M1 equals 3 kilograms, and that's going left or west at velocity V1F. And we have M2 equals 5 kilograms, that's going east at velocity V2F. All right, now you don't have to worry about the arrows too much. Usually you'll be able to figure out which way things will go. But even if for some reason you label the arrow wrong, going the wrong way, you'll find out in the end after doing the math which way it should go. All right, so this is our diagram of what happens after the elastic collision. Let's look at the situation of momentum and kinetic energy and relative velocity after the collision. Here's what we have. PF equals M1 V1F plus M2 V2F, which equals 3.0 V1F plus 5.0 V2F. And that equals negative 18.0. I know that it's negative 18 because I know that momentum is conserved. Then we have the final kinetic energy, KEF equals 1/2 M1 V1F squared plus 1/2 M2 V2F squared. And that equals 1/2 3.0 times V1F squared plus 1/2 5.0 times V2F squared. And that equals 114 joules. I know it's 114 because I know that kinetic energy is also conserved in elastic collisions. And finally, the most helpful thing, as we're going to see why it's helpful, is that the relative velocity also stays the same. Okay, so why V2F minus V1I? Because it looks like V2F is going to be positive, and so I can just do the positive minus the negative, because V1F is going to be negative, and positive minus negative will give us that positive 10 meters per second. Because even though initially they're approaching each other at 10 meters per second, after the collision they'll be going away from each other at that relative velocity of 10 meters per second. Okay, the relative velocity before and after the collision remains the same. We're going to solve this by bringing forward two equations from the last slide, and we're going to use the two equations that are easiest to work with. The black equation here is the momentum equation, and the orange equation is the relative velocity equation. So we have these two equations, and we're going to solve the system. If you look at it, we have two equations for two unknowns, so we should be able to do it. All right, let x equals v1f and y equals v2f. Why are we doing this? We're just doing it to clean things up a little bit, since we can always just give variables whatever symbols we want. So x is easier to write than v1f, and y is easier to write than v2f. Now we're going to write the system as 3.0x plus 5.0y equals negative 18.0, and y minus x equals 10. Continuing with the solution, we have 3x plus 5y equals negative 18, y minus x equals 10. Now we can solve by substitution. We put y in terms of x, so y equals x plus 10. Now we're going to plug that in to the other equation, and then we will use some algebra to solve for x, and we find that x equals negative 8.5. Now we will put that negative 8.5 back into the orange equation to solve for y, and y is 1.5. And so we've now found that x, which is v1f, equals negative 8.5 meters per second, and y, which is v2f, equals 1.5 meters per second. So the problem is solved. Now, just for fun, let's check our answer in the energy equation, because remember, with an elastic collision, momentum is conserved, kinetic energy is conserved, and relative velocities are the same. Now, we used the conservation of momentum and the relative velocities to solve this problem, but we didn't use the energy equation. We didn't need to, because that energy equation was used to derive the relative velocity thing. But let's just make sure that it checks out. So if we use that energy equation, 1.5 x squared plus 2.5 y squared equals 114, which we calculated on a previous slide, and we plug in the x and y that we just found, we see that indeed it checks out, and that means that the x and y are correct. And certainly we can see also that kinetic energy has been conserved in this elastic collision. It works. All right, and so what I recommend for you whenever you do problems like this is just use the relative velocity equation. V1I minus V2I equals V2F minus V1F. You can use that equation, and you can use the momentum equation, and that will be a simple system to solve. Final diagram, we have the red ball going to the left, so that's negative 8.5 meters per second, and we have the green ball going to the right, 1.5 meters per second. All right, let's look at this animation to get a better feel for elastic collisions. Here we have a red ball 1, and that red ball 1 is going to the right with a velocity of 1.50 meters per second. The green ball is at rest. Notice that if we look at the relative velocity between the two, well, we just have 1.50 minus 0, and so that's just going to be 1.5. And then if we look at the momentum, well, the total momentum of the system is all going to be ball 1's contribution because ball 2 is at rest. So we have a momentum of 3.75 kilograms meters per second and a velocity of 1.50 meters per second. All right, now let's see what happens when we play this. So we play it. Okay, look at what happened. So there was the collision. The red ball lost a lot of velocity because it transferred a great deal of its momentum to the green ball. The green ball was at rest and now has a large velocity. But look at the relative velocity first. Well, 1.88 minus 0.38 is 1.50. So we have the same relative velocity. And look at the momentum. Ball 1's momentum is now 0.94 kilograms meters per second. Ball 2's is 2.81. But when you add those together, you can prove it to yourself on your calculator, you get 3.75. And so momentum has been conserved. All right, we're going to try a couple of different values. Let's keep the masses the same, but let's say that the green ball is going to be coming to the left, so I'm putting a negative velocity for the green ball. And we'll say that it's negative 2.00 meters per second. I'm going to just separate these a little bit. Okay, a little separation there. Now we can clearly see the velocity vectors. We see that ball 2 has a velocity of negative 2.00 meters per second, ball 1, 1.50 positive. Okay, now before we do the collision, let's take a look at the total momentum and the relative velocity. Well, if we look over here, let's look at the total momentum. Ball 1's momentum is 3.75. Ball 2's is negative 3.00. Adding those together, you get a total momentum of 0.75. Now let's look at the relative velocities. If I do V1I minus V2I, I have 1.50 minus negative 2.00, and that gives us 3.50. So the relative velocity is 3.50 meters per second before the collision. Now let's do the collision and see what happens. All right, so the collision happened. The green ball bounced off the red ball and vice versa, so they bounced off each other and then went in opposite directions compared to how they were going before the collision. And so they went off in opposite directions. Let's take a look again at total momentum and relative velocity. Looking first at the total momentum, well, now the red ball has a momentum of negative 2.81 kilograms meters per second. The green ball 3.56. But add those together, and what do you get? you get 0.75. And so the overall momentum of the system has remained unchanged. And let's look at the relative velocities as well. Well, if you look at these relative velocities, notice that now we have the red ball going at a velocity of negative 1.12 meters per second. And then we have the green ball going at a positive velocity of 2.38 meters per second. And then if you do 2.38 minus negative 1.12, what do you get? 3.5. And so we get exactly the same relative velocity. All right, so all this has been to just look at some collisions and see in action some things that we've already learned. Now the last thing we're going to do is we're going to do an animation where you have to use it as a problem, and you're going to have to use the same method that I showed you for the first example of the red and green ball. That same method of using the momentum equation and the relative velocity equation, you're going to use that method to find out what the final velocities are for the collision that I'm about to give you. Okay, so we'll keep the same masses. Let's change a little bit the velocities. All right, so let's do this. We'll make that 2.5. So we have the red ball going at a velocity of 2.50 meters per second to the right. And we can change the mass just for fun. Let's change that to, let's make it 3.0. And then we look at the green ball down here. Let's make that 2.5. And let's give it a velocity of negative 3. Okay, have some separation here so we can see everything. All right, so this is the initial state. We have the red ball with a mass of 3 kilograms. We have the red ball's velocity as 2.50 meters per second to the right. We have the green ball with a mass of 2.50 kilograms, and the velocity is negative 3.00 meters per second to the left. Notice that this momentum is interesting. We have a 7.50 kilogram meters per second momentum for ball 1 and a negative 7.50 kilogram meters per second momentum for ball 2. And that means when you add them together, you get an overall momentum of 0. And that's going to be true before and after the collision. And also remember that the relative velocities will be the same before and after the collision. Okay, so the relative velocities then, as you remember from the example that I worked through, is just v1i minus v2i equals v2f minus v1f. All right, so using the steps and the method that I showed you earlier for the first elastic collision example that we did, I want you to do the same thing, follow the same steps. So you're going to pause the video and figure out on your own what the final velocity of ball 1 is and the final velocity of ball 2 is after the collision happens. All right, and then after you do that, I'm going to play and you can check and see if you were right. All right, so pause the video, do that on your own, and then resume when you have your answer. Okay, so let's play and see if you were right. Notice how our relative velocity here, v1i minus v2i, is going to be 5.50 meters per second, and my overall momentum is 0. That's got to be true before and after the collision. So let's play and see what happens. All right. So what we have here is we have a final velocity of negative 2.50 meters per second for the red ball and 3.00 meters per second for the green ball. And if you did the steps right, using the conservation of momentum equations and the relative velocity equations, then you should have gotten this answer, and you should have gotten these final velocities. All right, and let's do one more for practice. Here the red ball is 4.00 kilograms, velocity of 1.50 meters per second Green ball, 5.00 kilograms, velocity negative 2.00 meters per second. Notice again there's an overall momentum, and the overall momentum is going to be negative 4 kilograms meters per second. Notice also that there's a relative velocity. 1.5 minus negative 2 is 3.5 meters per second. All right, so using the same method, you're going to pause the video and then you're going to try to find out the final velocities of ball 1 and ball 2. That is the velocities they have after this elastic collision. So pause the video, do that now, and resume when you have your answer. All right, let's see if you got the right answer. We're going to play, and look what happened. All right, the collision happened, and then at the end, the red ball had a velocity of negative 2.39 meters per second. Green ball, a velocity of 1.11 meters per second. Notice how the relative velocities are preserved, because 1.11 minus negative 2.39 is 3.5. And notice how the overall momentum was conserved. And we have an overall momentum of negative 4 kilograms meters per second. You can see that just by adding these two. All right, so these are the types of problems we'll do in class. These are important problems, elastic collisions. And momentum in general is one of those fundamental concepts of the universe that we'll keep seeing over and over again.
Here's the classwork. Please write these numbers down. When I say also find the force next to number 7, that just means I'm adding to the directions a little bit. All right, see you in class.